1 system modeling, water tank system. In this system, we will use water flow control, considering the water entering the tank through the pump and the water exiting the tank through the valve. The important parameters of this system are as follows. Input, desired water level, measured water level from sensor. Output, control of water inflow, control of water outflow from the tank. System simulation in MATLAB. Response analysis. In a first-order system, the response behavior is as follows. When there is a change in the input, the water level in the tank will gradually increase by a value of P and will reach its maximum level over time, taking tau to reach this level approximately 63% of its full value. This system has an exponential response, which can be represented by the step response or impulse response. Two-system analysis. 2.1 time domain analysis. Time domain analysis considers the response of the system to changes in inputs, such as step inputs or impulse inputs that change abruptly. This analysis often looks at the response of the system in terms of response time, delay, overshoot, and settling time, which reflect the speed and stability of the system. Step response. The system response when a step input is triggered, such as turning on a pump when the water level starts to rise from 0 and reaches a constant value. This display shows the complete response characteristics in time. 2.2 Frequency domain analysis. Frequency domain analysis looks at the behavior of the system in terms of different frequencies using Bode plot and Nyquist plot tools to see how the gain margin and phase margin are, which helps us to know the stability and response at different frequencies. Bode plot. A Bode plot shows a graph of gain and phase versus frequency, which helps to understand the behavior of the system in terms of response to signals at different frequencies. It is often used to check stability margins, such as gain margin and phase margin. 2.3 Nyquist plot. Nyquist plot is used to show the behavior of a system in terms of its response to a signal with a frequency ranging from 0 to infinity. Using Nyquist plot can help to check stability by checking if there is a crossing of the -1 point, which is related to the stability criterion of the system. 2.4 Z-domain. Convert to Z-domain with Tustin. Use digital PID controller. Analyze with Bode plot and step response. 3. Controller design. Design all 3 types of PI, PD, PID controllers. Display KP, key, KD parameters. Use PID tuner and adjust bandwidth phase margin value.
Simulation and results. 4.1 Response curves. Simulating the response of a PID-controlled system allows us to see how the system behaves in response to step inputs, showing the response over time, such as rise, overshoot, settling, and changes in the water level in the tank. 4.2 Step response simulation. Step response is an analysis that shows us how the system will respond in the event of an immediate change, such as turning on a pump. 4.3 displays the response of the PID-controlled system and displays values such as rise time, overshoot, settling time when using a PID controller, proportional integral derivative, to control the water level in a water tank. The system will respond to changes in the step input or changes in the input signal that occur immediately. We will analyze the behavior of the system such as rise time, overshoot, settling time, and steady-state error. Step response of a PID-controlled system. The response of a PID-controlled system in the time domain can be analyzed from the step response graph, which will help us see the change in the water level in the tank when the command is given to increase the water level immediately. The behavior will be as follows. Rise time. The time to rise to 90% of the desired value overshoot, the value that exceeds the constant value settling time. The time taken to set a constant value after the system has tried to work steady-state error, an error that occurs in the long term. The PID controller performed best with a fast response and minimal overshoot, followed by the PD and PI controllers. Conclusion: the PID controller proved most effective for this application, maintaining the desired water level with fast settling time and minimal overshoot.